We ended last time with this position time plot and these two possibilities and what they might mean. So if we look at the curve number 1, this line sloping downward, all this means is that as time goes on, we find the object at lower and lower locations. So a position time plot like this simply means the object is moving to the left. At some point in time, it crosses the 0 mark and kind of keeps going. And then we find it on the left side of the 0 mark that we might mark out -1 and so on. The second curve, the object starts off slowly, and we know slowly because the slope of this position time plot is shallow, kind of like over here, and then the slope increases over time. So we have a slope right here early on, that's like that, and we have a slope later on, that's like that. The slope is higher later on, so this is speeding up and going to the right. This one is a constant speed to the left. And that's what both of those are. Now, if we're going to be dealing with cases where the speed is not constant, it makes sense to introduce another type of plot, and namely a speed time plot. So we're going to have two types of plots now. A position time plot and a speed time plot. Now the time here is the same, but the speed time plot has speed on the y-axis, and the position time plot has the location, the position on the y-axis. If we go back to our original example, we started an object at 2 meters, and every second increased by 2 meters. We saw that we had a straight line. If at some time, we'd like to know what is the position. We want an equation that relates the position at any given time to the various quantities, one of them being the initial position, which I'll denote with an x0, time, of course, and also the speed. And if you recall, the speed here is the slope of the position time plot, and in this case it's 2 meters every single second. This is an equation of a line, so we can write out the kind of y equals mx plus b form. So we have the final position, the position that we would have is equal to the slope, which is the speed, times the time, plus the initial, plus the intercept here, which is the initial position. Now, what does this look like on a speed time plot? Well, here the speed is constant. It starts off at 2 meters per second, and it's constant. So it goes like that. So this is 1 meters per second, 2 meters per second, 3 meters per second, and this is not changing at all. It turns out that the position of the object, or the distance traveled of this object, is equal to the area under the curve. So the distance traveled by the object is equal to the area under the speed time plot, which means the final position should be equal to the initial position plus that distance traveled. final position we're just calling x, initial position we're calling x0, and the distance traveled is the area under the curve. So at some given time, this is here the constant speed. We simply have a rectangle, base times height. The base is the time, the height is this constant speed, is called v0. So it's the same equation in both cases. Now this idea, which is very important, works for any shape of a speed-time plot. So if we are looking at an object that is increasing in speed over time, we could have something like the following. We could have, after 1, 2, 3, 4, 5, etc., 4, 5, 6, we could have a line that in, say, 4 seconds, we've gone up to 6 meters per second, and the speed itself is changing. At first it's at 2 meters per second, and later on it is at 4, and later on it's at 5, and then later on it's at 6, and so on. So this is changing. The slope of a speed time plot is what's called the acceleration. So in this case, we have a change in speed of, in this case, 2 to 6, so of 4 meters per second in 4 seconds. So we're actually changing 1 meters per second every single second. So at some point in time, I might be interested in knowing how far the object has traveled, even though it has increased in speed over time. So how do we do that? Well, we do exactly the same thing here, and we need to find out the area under this curve. So the area under this curve includes this initial part, and it includes this triangle. So we have the final position is the initial position plus the distance traveled, and we can break this up into two shapes. So here we have the rectangle, and so we have the initial speed, that's where it's starting, times the time. This is the base times the height. Okay. And now we have a triangle, so the area is 1/2 the base times the height. Okay. So what is the height in this case? In order to do this, we need to express it in terms of the final position, final speed, and the initial speed. So it's this difference, that's the height. So we have the final speed minus the initial speed. Now, of course, we don't know that, and we don't know the position, so we have some more work to do. This part of it, the final speed, if we know this is a line, we can do the equation of a line, the y equals mx plus b form for the speed itself, which would be, the final speed is the initial speed, that's the intercept, plus the slope times time, which is the x-axis, and the slope is the acceleration. So we have that. So this quantity can get plugged in right there, and then everything is in terms of constant quantities other than time. So then in this case, we can get x0 plus v0 times t plus 1/2 times t times, and I'm going to put this part of it, v0 plus a times t, put that part minus v0. Now these two v0s cancel, and then I can bring the t over, and I'm only left with this one term, so I end up with x0, the initial position. We have the initial speed times time plus 1/2 times the acceleration times time squared. So we end up with this form, and that is the form for a parabola, so we would get something on the position time plot that would start off, possibly, if it's at 2 meters per second, it'd start off with this slope, and then it would increase in slope, and it would go up like that, and increase in speed as it does so. Another way to do this as well is to go back to this form and rewrite it in the following way. So we'll just expand out this form. So I get x is equal to x0 plus v0t plus 1/2 t times v minus 1/2 t times v0. And notice these two terms are basically the same. We have 1 v0t and a minus 1/2 v0t. So this ends up being a positive 1/2 v0t, and I can combine it. So this, you can see, is the following: plus v plus v0 over 2 all times time. So you can rework this form into this form, where this is simply the average of the initial speed and the final speed. And it's the average speed of the object. It happens to have this nice easy form of the beginning plus the end over 2 because we have a straight line. If it wasn't a straight line, we could still use the average speed, but taking the average would be a little bit harder. If it wasn't a straight line, we could also do the same thing and maybe not get a single nice equation, but we could break up any curve at all into smaller little areas. So we could figure out how far something went by simply looking at the area under the curve, no matter how crazy the line was, by breaking it up into squares and rectangles and triangles and other shapes. So it is that part of it, the area under the curve is quite general.